basic procedure of problem solving. I use one simple example to show you the basic procedure of problem solving. Because for this class, what we are doing here, basically, we do problem solving on computing problems. So we need to do a lot of logic thinking. I will give you many problem-solving strategies. Those strategies usually very simple, but you need some practice. All right, so let's start. First, let's look at the question. Look at this question. So we have a standard chessboard, 8 by 8. Okay, the grid, black, white squares, grid. Okay, the question: how many squares of different sizes can you find along the grid of a chessboard? For example, this is a square, right? This is a square with a size 2 by 2. Okay? So you can see another one 3 by 3 here, right? So you have so many different squares. Let's look at another one. 6 by 6, right? So the question, you need to tell me how many squares of different sizes you can find in a standard chessboard. That's the question. So we treat it as a computing problem. Okay? So we do some computation. So computing problem. Okay? All right. So in the real world, let's just assume we have this problem in the real world. We need to find a solution to this problem. Okay? So first, we need to understand the problem. We need to understand the environment we are working on. First, for a computing problem, basically what we are doing, data processing. All right? So what we are doing actually is the data processing. Okay? So here, I want to ask you, because when we do the data processing, first we need to know what is our data, right? What is the data here? What kind of data we need to do processing? So can you tell me what's the data? Yes. Squares of all different sizes. That's the data. Okay? That's the data we need to do processing. Okay? All right. So what kind of processing? Counting. Do counting. Counting. Number of squares. All right. Yeah. So then, after that, another question. How to identify all the squares? Okay? Yeah. Can you find some rules to identify all the squares? Yeah. Find the rules. Yeah. Although here we can use eyes, we can identify, but it's hard to use your eyes to find all the squares, right? Yeah. So we need to find some rules to help us identify all the squares. Then we can apply the rules to do the counting. Yeah. So can you tell me how to identify a square? Yeah. All right. Yeah. You? Yes. Yeah. Yeah. So based on your intuition, so you describe based on your intuition. All right. Yeah. All right. But we want to use some clear way to identify. Okay? Yeah. So we want to describe four sides. Yeah. Can you see? Oh, yeah, 2 by 2 just one. Yeah. Oh, 2 by, no. 2 by 2, you have many 2 by 2, right? We need to count, no, not just one. All 2 by 2s, all 3 by 3s, all 4 by 4s. Okay? Not just the size. So what do you give me? Number of sizes, right? Number of different sizes. 2 by 2, one size. Okay? One size. But here, we need a number of squares, not number of sizes of squares. Okay? Yeah? All right. So let's still answer the question how to identify a square using a better way. Yeah. Although everyone, you know how to identify, but you may not be able to describe it clearly, right? We want to have a clear way to describe it. Yeah. Let's use 4 sides to describe it. Can we use 4 sides? So there are 2 horizontal sides and 2 vertical sides, right? So if you can get 2 horizontal lines and 2 vertical lines, but you also need to know the distance between 2 vertical lines and the 2 horizontal lines should be the same. Yeah, that's our description of a square. Okay, use 2 horizontal lines, 2 vertical lines with the same distance between those 2 lines. Yeah, to identify. Okay, one square. Okay, yeah. All right. Now, so here, what I'm doing here, we want to understand our problem, right? So what we're doing here, that's the understanding part. Yeah. Before you solve the problem, you need to spend a lot of time to understand your problem. The better you can understand your problem, the better you can solve the problem. Okay, so that's so at the beginning, so we need to be very patient to understand the problem. Okay, all right, we still need to do more in understanding. Yeah. Next, now the critical step. Now we need to work on our data. Yeah. But when we work on our data, the question, how do we work on the data? Yeah. What is a better way to work on the data? Okay? Yeah. So that's the next question, critical step. Yeah. All right. How to manipulate the data efficiently. Yeah. At this point, your view on the data, pretty messy, right? Yeah, because the squares of all those different sizes spread like random, in a random way, right? Yeah, very messy. Yeah, that's pretty much like our real world situation. The original data given in a random way. Okay? It is not easy to work on the random data immediately. Okay? Very messy. We don't know how to get started. So that's the general situation in the real world applications. All right, so here, what do we need to do? First thing, organize the data. Organize the data. Okay? Yeah? So, make it easy to manipulate. When you organize the data well, it's much easier to work on it, to manipulate your data. All right, so let's think about how to organize the data. Yeah. So here, we want to arrange the data in a well-organized way. But this is very abstract, right? What's the specific way you want to do to organize your data? Okay? Yeah. Typically, yeah. So for the general problem solving, typically to organize the data, you do characterization. Characterization. Put your data in different categories. Put your data in different categories. That's a typical way. Okay? Although there are other ways. Okay? Later you will see we have other ways to organize data. Yeah. So this is one of the commonly used ways. Characterize, put them into different categories. Can you think about what kind of categories we want to use here? Sizes, right? Different sizes of square. Yes. Each category, we only look at the squares of the same size. For example, 2 by 2, that's one category. Okay? 3 by 3, another category. Yeah. The reason we use different categories to organize the data, because in the same category, we can find the representation for the number of squares. Same category, we can find the representations, formulas for the number of squares in the same category. If you do not do the characterization, then it's hard to use one formula to represent number of squares, right? It's hard, okay? So that's the reason. So we want to do the characterization. All right. Yeah, so here, suitable categories, so the data in the same category share the same property. Yeah. Because the squares of the same sizes, we can find the same rules for them, right? Same rules for the squares of same sizes. Yeah. So then we can find the representation quickly. Yeah. All right. All right, so here, let's list all the possible sizes. Yeah. Total, these 8 different sizes. Yeah. All right, so next, now we need to do the counting in each category. Yeah. All right, so the main work, let's do the counting work here. Okay, squares in various sizes. Yeah. So let me do a chart here. The first column, the size. So we list all these sizes. Yeah. The second column, let us count the number of squares. How many squares of size 1 by 1? 64. Okay, 64. Yeah. Easy. Yeah. So let me write 8 by 8. Okay, 8 by 8. Yeah. All right. How many squares of size 2 by 2? 16? 49? Good. Can you think of a question? Sorry?
4 by 4.
Oh, 4 by 4. 4 by 4, 16. 4 by 4, 16, right? Yeah. All right. So for your answer, 4 by 4, yeah, I understand. Yeah, because, so here, 4, 1, 2, 3, right, yeah. Because when you look at here, 1, you do the split like this, 4, right? That 4 by 4, yeah. But the question, we want to count 2 by 2 squares in any position. Any position. We do not require them not overlap it. So here, in your understanding, you assume these 2 by 2 squares cannot be overlapped. We don't say that, right? We allow those 2 by 2 squares, they can be overlapped. Okay? That means, how about this 2 by 2 square? Is it legal? Right? Legal, right? How about this 2 by 2 squares? Right? Also legal, right? Yeah. All right. So now we allow overlapping so we can have more squares. Yeah. All right. So here, let's do the counting in this way. Yeah. A square is determined by two dimensions, right? Horizontal dimension, vertical dimension. Let's separate those two dimensions. Let's look at the horizontal dimension first, then vertical dimension, okay? Let's do the counting. To get a 2 by 2 square, we just look at the horizontal dimension, how many different line segments we can choose to form one 2 by 2 square, okay? Horizontal dimension. Is this one, first one, okay? Is this second one, second, okay? Third one, all right? Fourth one, fifth, sixth, seventh, okay? So horizontally, we can find 7 different line segments that can be used to form a 2 by 2 square. How about the vertical dimension? Vertical dimension, the same, right? Yeah, same. Yeah, because they're symmetric, right? Horizontal, so you flip, you get a vertical. Okay? Flip, okay? Symmetric, okay? Yeah. 7 by 7. So one student said at the beginning 49, right? Yeah. So that's how you get 49. 7 by 7. Okay? All right. So the answer, second category, 7 by 7. Yeah. How about 3 by 3? 3 by 3. 6 by 6? Do you agree? 6 by 6? Yeah, 6 by 6, correct. 4 by 4. How about 4 by 4? Find some rule. 4 by 4, how many? 5 by 5. 5 by 5, 4 by 4. 6 by 6, 3 by 3. Yeah? So many of you got the rule. The last one, A by A, whole chessboard, right? Only one. Okay, all right. Yeah. See? Yeah. After this list, can you find the total number of squares? Yeah, it's easy, right? Adding up all the subtotals, okay? You get a total number of squares. Yeah. So here you can see how important to organize the data, right? Yeah, all right. So here, there is another, because when we figure out the number of squares in each size, we observe a rule. Yeah, we observe a rule. Yeah. Yeah. Because after we did 7 by 7, then we do not need to do things like this each time, right? So basically, we do induction, okay? So for the remaining, when we count the number of squares in the remaining categories, what do we did? Induction. Yeah. Because we follow some rule. We observe a special rule here. Yeah. So what's that rule? Here I want to summarize that rule. Okay? Yeah, there is a rule there. Okay? Yeah. That is, first, we represent the size, m by m as the size. Okay? So we use a variable m to represent the sizes, m by m. Any size. Then, the number of squares, we use another variable to represent number of squares, m by n. Can you tell me what is the relationship between m and n? There is a rule. So what's that relationship? M and n. Some interesting property there. M and n. M plus n equals 9, right? M plus n equals 9. Can you see that? You just add those two numbers. Yeah. 1 plus 8 equals 9. 2 plus 7 equals 9. 3 plus 6 equals 9, and so on. Okay? So for each row, you add up those two numbers, m number and n number. It's a constant, 9. How about this rule? Okay? Yeah. So this rule, in this question, we use a concept to represent it. A concept. Yeah. All right. Because this is a fixed number. When you change the sizes, this number never changes. It's an important property. Okay? Yeah. So we introduce a concept for this quantity, fixed number quantity, invariance. Invariance concept. Okay? Yeah. So here I introduce, in problem solving, sometimes there is a hidden property. This hidden property very important. Yeah. So here we call the invariance property. It's hidden. You need to discover it. Yeah. Yeah. You need to discover the hidden property, invariance. Yeah. But after you find the invariance, then it's useful. Then this invariance property is useful in our problem solving. Yeah. All right. Understand the role of the invariance. Yeah. Yeah. All right. So usually invariance give us the critical property to solve the problem. Okay? So if you can get that invariance, then you're almost halfway solving the problem. Yeah. So that's how important this concept is. Yeah. All right. So here, one important way to use the invariance, that's we can use it, keep track of the data. Invariance property can help us keep track of the data. Okay? What's that? Because when you have large amount of data, you may get lost, right? When you navigate into your data, you may get lost. Okay? That's possible. Okay? Yeah. Here, let me show you a simple example. When you get lost, you need this invariance property to help you get a location where you are. You need to get that information based on the invariance. Okay? Here, let me show you a simple example. When you get lost, okay? Yeah. You need help from this invariance. Let's imagine we consider an extended chessboard, 100 by 100 chessboard. Okay? Yeah. So it's a very large extended chessboard. Okay? Grid. 100 by 100, grid. Yeah. All right. Yeah. So we have a lot of data there. Yeah. Then it's very easy to get lost, right? When you try to, study your data, very easy to get lost. Now let me ask you one question here. Yeah. If you can, find your location in the 100 by 100 grid. Yeah. The question, how many squares are of the size 37 by 37? 37 by 37. Based on what we have learned so far. Okay? Yeah. We get experience. Yeah.
64 by 64.
Correct. He got it. 64 by 64. Other students, can you see that? Why 64 by 64? Yeah. Yes, I can understand what you mean. Yeah.
So is it because like in that previous one you counted up to 9, so here it's like you count up to 101?
Correct. 101. The invariance is 101. M plus n equals 1 more than the, right, size of the total big board, all right? 64 by 64. So here you can see that's the role of the invariance. Yeah, yeah, because when you get lost, yeah, so you need help from this critical property. That's what we call it, critical property. Okay, yeah, yeah, things like that. Yeah, all right. Yeah, okay. Yeah. So now. Yeah. But finding invariance usually is very difficult. Yeah. So you need to really understand the problem very well. Yeah. Sometimes it is buried very deep. Yeah. Invariance property is buried very deep. So you really need to understand extremely well. You can discover that invariance property. Okay? Yeah. I have another good example. Yeah. I have another good example about the invariance property. Yeah, but I do not give you here. In order to save time, I do not give you here. Yeah. If later I have some chance, I can show you another. Also based on chessboard. Also based on chessboard. But in that example, very hard to find invariance. Yeah. Yeah. So I can post that puzzle question. It's a puzzle question. I can post that puzzle question as a, in a video. Yeah, I explain it in a video, so you can, play around. Okay, so think about it. Yeah, for example, in the Labor Day weekend. So you just think about. Yeah, so I post that video. Okay, for your Labor Day weekend. Yeah, so think about. How can you find invariance? Another chessboard puzzle problem. Okay, chessboard puzzle problem. Yeah. Here I do not, because we want to save some time. Okay, so I do not talk about that here. Yeah. Then, calculation. Complete the computation work. Yeah. 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 So for the given question, we just do the summation on these 8 square numbers. Yeah. So we get 204. Yeah. All right. Yeah. But if we want to consider a general problem, we want to count the number of total squares in an n by n chessboard. This time we consider n by n chessboard. Okay? So I ask you to give me the summation. Yeah. So you can write a formula like this. Yeah. N by n squares. Okay? Yeah. So 1 square plus 2 square, consecutive square numbers. So we add up these n consecutive square numbers. Yeah. Do you know the formula? Any of you?
Would be a summation of 1 to n of m squared.
1 to m's.
Like the summation.
Yeah, summation. Correct.
1 to n.
1, yeah. 1, you mean this, right?
Yes.
And what else?
Squared would be the equation.
Yeah, and okay, yeah. So what do you give me? So you want to say this, right? Is it you want?
The bottom is 1.
Right.
Yeah.
Yeah, yeah. Usually we write this way. Yeah. So this is a representation. This is not a formula. Okay. All right. So we want to write the final formula in terms of n. We want to write a formula in terms of n to give us the total. This one. 1/6 times n plus 1, parenthesis, times 2n plus 1. Okay? Did you see it in your discrete math course? Yeah. Yeah. In appendix. Yeah. So, later part. Yeah. Because in discrete math, you do 1 plus 2 plus 3. Did you do this? Did you do this? Yeah. Yeah. If any of you still have the book, you can go back and check. This is one formula, okay? Next one, this one. See? Yeah. Then cube, okay? So I don't know if you talk about the cube formula. Yeah. Here, I do not give you the cube formula, okay? All right. But if I give you the cube formula, it's very easy to memorize the cube formula, okay? Yeah. Let me write the cube formula. 1 cube plus 2 cube dot 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 plus n cube. The formula is so easy, okay? Yeah. What's that? This formula, we take square, all right? 1/2 n plus 1 squared. That's the cube formula, okay? Yeah. See? Cube formula, okay? Yeah? Yeah. Yeah. How to find it? Yeah, how to find it, that's another story, okay? How to find it, another story, okay? Yeah. If you are very interested, you can go back to check your discrete math textbook, okay? Yeah. All right, yeah. All right, yeah. Let's move on, yeah. Summary, okay, after we solve this problem. So let's do some summary. We have learned 3 important knowledge points. The first one, invariance property, okay? Yeah. M plus n equals capital N plus 1. This property, okay? Our first knowledge point, okay? Yeah. Second one, sum of squares, that formula. Okay? Yeah. So that formula. Yeah. We'll learn. Yeah. The third one, invariance. Yeah. So the general invariance. Yeah. The first one, that's the specific invariance. But here we talk about the general invariance property. Okay? Yeah. So in a problem containing the data that is not organized well, one can discover certain invariance property to help keep track of the data or find other useful properties. Yeah. Keep track of data, just one of the usages. Yeah. We can use invariance property to do many other things. Yeah. Yeah. Okay. Yeah. All right. Yeah. So now I complete 8.2. Okay. Yeah. I complete 8.2. So I can start part B.